Hello everyone, this video is the solution video to homework 2. Now, we actually did look at the system in homework 1. Now we're basically going to continue on that because we didn't quite get a good controller design in homework 1. That was not really the aim there. But here we are actually focused on the PID controller, which we hope that will achieve the 4-second settling time requirement and the overshoot of 10%, of course. Now, again, the same is going to be happening for this homework 2, where you are going to basically look at all the questions and then refer to this TF-ZBK and the step response, etc. I'm going to do my best in creating the plots, but sometimes I might skip the pole zero map here because I'm trying to explain you the solution here and I'm not creating a report myself. So let's dive into the first question, which asks us to design a PID controller and to define all the stabilizing PID controllers in terms of KI that give basically 4-second settling time and 10% overshoot, hopefully. Now, when we are going to design a PID controller, it's best to note that we should actually define the controller parameters linearly. And that comes from the fact that we are going to use the algebraic method where we use polynomials and their coefficients and equate them to each other. So if it's possible, you should go with the linear representation. It could be the case where you could just choose k, z1 and z2, where z1 and z2 are the zeros of the controller and k is the gain of the controller. But it doesn't really make sense in this case to use this representation because we would end up in the multiplication of z1 and z2 and even k times z1 and z2, which is highly nonlinear and we want to avoid that. And it's also important to note that z1 and z2 should be complex numbers in this case because that would be the general case. But here, if we look at them as the coefficients of a polynomial, then it's not going to be restricted to be complex, or we don't really have to take that into account because the coefficients will be always real, but the solution of the polynomial itself, so the zeros of this controller, could be complex. So we're kind of in the most general case, but it is going to be linear. So let's state our PID controller, which would look like KD times S squared plus KP times S plus KI divided by S. So therefore, we would also look at the closed loop transfer function, which would be FSS times GSS divided by 1 plus FSS times GSS. So then we would decompose this transfer function into its zero polynomial and characteristic polynomial, or in other words, the numerator and denominator. Now it's quite important to note that PZS is the zero polynomial, PCS is the characteristic polynomial here. Now we have PCS, and if we run this, we should get basically the characteristic polynomial that looks like this. Of course, I already have copied the previous work on homework 1 where we did calculate zeta and omega n, so I'm skipping that part. That should be already obvious here. And therefore, we also have PDS defined here. I am going to basically define the residual polynomial PES and going to solve the problem here. Now, well, you can see that this is a second-order polynomial. Our closed loop is a fourth-order polynomial, which leaves us with a second-order residue polynomial. But it is again important to choose the polynomial representation wisely. Here I'm using s squared plus as plus b, where sims a and b are again real. I'm doing basically the same thing that I did here. I'm choosing the coefficients rather than the roots of the polynomial because this makes more sense for the algebraic method. Then we're going to form our problem where all the coefficients of PCS should be equal to the coefficients of PDS times PES all the S coefficients here. Since we're going to generate a report, or you might go and generate a report, let's also display stuff that might be relevant to our report. So we could also solve the problem, but we need to provide MATLAB which variables are important, and if in this, as it is in this case, if we have more unknowns than equations, then we might leave out one of them to indicate that we are solving the solution, or we want the solution in terms of that free parameter. In this case, we have Ki. So we want MATLAB to solve us KD, KP, A, and B in terms of Ki. So I omitted Ki so that MATLAB knows that Ki should be the free parameter here. So let's run this basically, and we end up in the solution. Even if you wouldn't have MATLAB available to you, if you would have been in a final exam or midterm exam, you could still deal with this problem on your own, because you can see that Ki and B are proportional and they relate to each other with the coefficient 2.862. So you could just find B in terms of Ki and then plug in B here. And since A is obviously 6, you can plug in that too. So you would end up in Kp in terms of Ki. The same goes for this equation here, where A is known, B can be stated in terms of Ki. So if you plug that in, you could also acquire Kd. So it's not quite hard to get the solution, but this is not always the case, because this system for some reason has its numerical beauty here, where we can work out A, and we can then see that B and Ki are proportional to each other. This is the nicest case you might end up in. It would also be possible to get a different numerical value, which would rather bother us. For example, if this would have been negative, then we would conclude that there's no such PID controller that we can use. At least it's not going to be stable. And the reason behind that is that we actually have stated our residue polynomial in terms of A and B, where the coefficients are A and B. And we can basically conclude the stability based on PES. So you might think to yourself that maybe I could plug this into the transfer function itself, which we might do, for example, if we use substitute here and TSS here. There's a nice feature that is available to us that we can use here. We don't really have to indicate which parameter should be substituted with which value if we provide a struct to it. The solve method creates the struct, and we can just give it to the subs function, and it would look up all the possible field names with their values, and if that's substitutable into TSS, it will just carry out that operation. So therefore it can deal with this stuff on its own, and we don't really have to care about the solution. I sometimes like to define some placeholders. KD val equals double sol dot, or not double but sol dot KD, and I can go on with this with KP val, A val, and B val. But here it's not always necessary, and I like to keep things short here. So we could just provide sol to subs, and it will look up all the possible values and substitute them into it. So once I do this operation, once I run this command, TSS2 will only depend on Ki, and all the other parameters will be substituted in. So you can do that to the controller too, which is a nice feature in this case, because in the question we are asked to basically state the controller. So why should we not use it? Well, let me also give TSS2 here and run this. First of all, we might want to use some VPA on them in order to convert it into a readable format. So at least that's important. And we might also want to use pretty on them so that we get a better visual representation here. There we go. Now, in terms of the controller, it's quite nice. We can see that the KD parameter is this here, and then KP relates to KI with this expression here, and KI on its own is here. So this would be the parameter controller that we are looking at. But the closed loop transfer function is quite ugly, and we can solve that by running the simplify fraction command on TSS before we do anything else. So it would then get rid of these simplifications, and we would end up in this. Now, note that in the question, it says that we should define all the stabilizing PID controllers in terms of KI. So what we've done so far is we kind of solved the problem in terms of KI. We substituted this stuff back in, and we've acquired both the closed loop transfer function and the controller in terms of KI. But we didn't guarantee that this would be all the stabilizing controllers. There might be some values for KI that end up in unstable closed loop transfer functions. Now, in order to avoid that, we need to basically look at the characteristic polynomial here and do some study on it in order to conclude the stability interval for KI. But if you're in an exam, if this is without MATLAB, it would be a pain because, well, it's a fourth order polynomial, and writing down the root Hurwitz table and carrying out all the necessary steps is going to be time consuming. And it goes for almost all the stability analysis that you're going to do on this polynomial because it's a fourth order polynomial. And yeah, we cannot avoid some operations if we want to conclude the stability of the system. But there is a better way of analyzing the closed loop stability because we don't really have to check a fourth order polynomial in this case. And the reason behind that relies on the fact that we are using PDS times PES and the coefficients of this polynomial, and we equate that to PCS. So a part of PCS, or the closed loop transfer function characteristic polynomial, should have PDS, which is the desired polynomial, and by definition, if zeta and omega n is positive, and if they are real values, then PDS should be a stable polynomial. So it means that this portion here is guaranteed if zeta and omega n are positive. And for our case, we already have TS equals 4 overshoot 10%. We've already calculated that, and we can see that sigma, in fact, is going to be negative for both roots of this polynomial. So we know that PDS is already stable. If we analyze this whole system, we would be reanalyzing or reassessing the stability of PDS, which is not necessary. We could just focus on PES, which is the residual polynomial, which we added and we didn't do anything about it. We just used this polynomial and we didn't guarantee, or we didn't check if this is going to be stable or not. So we can do that by looking at this polynomial, which is a second order polynomial, and it is way easier to assess the stability of this polynomial rather than the whole transfer function. So if we do that, since this is a second order polynomial, what we can do is directly focus on its coefficients. If A is positive, which is, and it is in fact equal to 6 even, and if B is positive, then this polynomial is going to be a stable one. That would then point us out that the whole closed loop transfer function would be stable because PDS is already stable. So how can I just reduce this down to the positivity of coefficients? Is basically relying on the fact that the sum of the roots of this polynomial would be positive if A is positive. So this is going to be positive if A is positive, and their multiplication is also going to be positive if B is positive. So this means that we would end up in Well, if the multiplication is positive, by the way, I'm talking about s plus p1 times s plus p2 equals 0. So if we multiply them, and if this is positive, if their multiplication is positive, it means that they share the sign. It could be either positive, both positive, or both negative. And since their sum is going to be positive too, it would mean that the negative case will be eliminated. So both P1 and P2 should be positive values. And if that's the case, then S plus P1, P1 is positive, is equal to 0. So S is equal to minus P1 and S is equal to minus P2. P1, P2 being positive means negative real roots. So that's basically what we are trying to claim here. Or P1 and P2 could be complex, and it doesn't change, basically. It would be on the left half plane. This is only for second-order polynomials. This is necessary and sufficient for second-order polynomials. For third-order, you could check that, but that might not be sufficient. You might need some extra conditions on that because you have another extra root. This doesn't guarantee you, but it is still necessary to be true. So yeah, and here we can see, luckily, Ki and B are proportional, which means that if I want to state all the stabilizing PID controllers, I could just skip the whole transfer function thing here. I could just display another extra condition, which is Ki being positive. Strictly positive would make more sense because we would end up in having a root at the origin, and if it's at the origin, it's not stable because it would end up being a ramp response, and well, that's not at least bounded in terms of marginal stability, so we would not like to include it. So this PID controller with Ki positive is going to be all stabilizing PID controllers that are a candidate for our design, because we are not guaranteeing that they will have 4 seconds of settling time and overshoot of 10%, but what we could guarantee at least is that it will include a set of poles that should correspond to that. So our all stabilizing PID controllers, if we use this expression here with Ki positive, will have sigma plus minus j omega d as a set of roots, subset of roots, basically. And there will be also other poles and zeros, but at least the poles will be on the left half plane. And that's basically it. So this is the first part here. Now, for the second part, we are asked to obtain the PID controller that maximizes the dominance of the residue poles, and only the residue poles. So for that fact, we already are looking at PES. So what we can do, let me just copy this part here and call it residue. So this is going to be Q2, and there we go. Now, since we are already looking at PES, what we can do is we can use the same strategy, and we could substitute the solution into PES and look at the residue polynomial itself. So I'm basically substituting all the parametric values into this, and I might want to use VPA in order to, again, increase the readability. So there we go. Now, if you look at such a polynomial, you should recognize the fact that we have a polynomial and it depends on a certain controller parameter K. And what we're really interested in is that what happens if we change Ki to the roots? How will they move? How will they position themselves? Because we're interested in their distance to the dominant poles. We want to push these roots of the polynomial out of the dominant zone or region. So we're interested in that. So you might want to use some tabulation. You might plug in some Ki vector into this polynomial, look up the roots, and then like calculate stuff. But Yeah, we already have a tool for that. We already have a tool that uses certain controller parameter, varies it from 0 to infinity, and then shows us the exact movement of all the poles of the given polynomial. And that's called root locus plot. So we have to convert this or work on this polynomial a little bit to get a transfer function that we can then use to plot the root locus in order to analyze this polynomial. So it's quite easy to do it when you have just one unknown, which is the case for us now. So what I'm going to do is I'm going to look up the coefficients of our controller parameter instead of using the polynomial variable s, and I'm going to reorganize this into its ki terms and non-ki terms, and I'm going to divide the whole polynomial with the non-ki terms, which will then convert this into 1 plus k times g equals 0. So that's basically the whole idea, and let's basically do it. Let's use something temporary, use coefs on ps2 with ki and all the terms. So let me quickly show you what the result is. Well, we have a coefficient here, which should be 0.3495. And then we have the non-ki terms. So if I divide everything by the non-ki terms, this would become the numerator, this would become the denominator, and I could define my equivalent transfer function so that I can analyze this polynomial better. Now, therefore, I'm going to call it GE, TF, and then maybe double, and then the coefficients of the first value. This is going to be the k terms here. Get all the coefficients, and this is going to be the non-ki terms, and this should give me the transfer function that I'd like to have. You can see that if you look at ki ge divided by 1 plus ki times ge equals 0, you would end up in the characteristic polynomial that looks exactly like this. If you're in an exam, this method would give you almost the result, because it's quite powerful to have this root locus method available. Instead of using some numerical stuff without even using a calculator, we can see that when we are about to sketch the root locus of this transfer function, we have one pole at the origin, another pole at -6, and they will collide on the real axis at -3. One of them will go up 90 degrees and the other one will go down with 90 degrees, and that would be the root locus sketch of this transfer function. And when that's the case, we can already see what the dominance factor can be at maximum and what ki should be there for. So let me plot you the root locus plot here. So that might stay open. Let's have another figure. Call it 1, CLF. Maybe I need to introduce subplot already, and they should be side by side. And I'm going to basically open up hold on. That's enough, I guess. And the root locus of GE, because I will immediately choose a controller, and then I'm going to look at the step response. So therefore we have this here. So once we have this plot, we can see, as I've said before, one pole is at the origin, one pole is at -6, they will collide at -3, and one branch will go up, one branch will go down by 90 degrees. And yeah, I can also indicate the point that we're working with, because I have the necessary coordinates here. We know that we will be looking at sigma, omega d, and then this is basically the design point. Maybe add a certain line width to it. I even can plot the S-grid, which is zeta omega n, which indicates the exact position and polar coordinates of our design point. And we can see that this point is going to be, or the pole pair here will be the roots of PDS. And since this is a fourth order closed loop, we have two additional poles. One of them starts at the origin, one of them is at -6. They will collide here, and this is basically the critical point where from this point on, we will not change in terms of, or we cannot push them away, or they will not enter the zone back in. They stay at the boundary of the best possible dominance factor that we can acquire from this setup here. So it's going to be basically equal to 1 because I know that already the sigma value, the real root of our solution or pole pair, is -1, and we have -3 here, so there's a 3 times dominance factor in terms of the residue poles. So I could also plot a little line that would help me out in indicating that times 1, 2, and then the y limits, and it should be k. Yeah, that is actually okay, I guess. So this is basically the real value of our pole pair, and we can see that it is exactly -1, and we are at -3. We can push both poles to -3, and we can even push further than that, and it will not change in terms of dominance factor. Of course, it will have an effect on the system's behavior, but in terms of dominance factor, it would be constant and it would be equal to 3. Now, the critical point here is important. Before that, we cannot really use the gain that is lower than this critical point here. And the reason for that is that this pole here starts at the origin and is the dominant thing when Ki is low. So for low gain, we will have actually this behavior here. And it will reach to the real value of -1. They will be aligned here. And after that, it will go away, start going out of the dominant region. But the furthest point is going to be here in terms of real axis distance. Yeah, therefore, the conclusion here is that we can use basically this point or greater Ki values than this point for residue pole dominance. We actually can, by the way, calculate it quite easily. Again, if we're in an exam, we can use the gain condition here. We can see that the distance from here to here is 3. The distance here is again 3. So their multiplication would give us 9. But we have a coefficient here. So 9 divided by 0.3495. 9 divided by 0.3495 should give us 2575, which is, when you click on this, exactly the point that we're looking for. Of course, this is rounded, but this is the exact value. So I'm going to basically use this. So we can state that Ki val is going to be this or greater than this. And our controller is going to be basically this. So let me just take this, state the same. But now this is going to be greater than equal to string Ki val. That's going to be only the difference. Whilst I'm at it, what I can do is I can just get the controller, the corresponding controller here. I can use substitute instead of FSS2. I believe we have that somewhere. And instead of Ki, we will use Ki val. And I have my own functions, tf to sim, sim to tf. You can code them too. Sim to tf is going to be suitable here. I'm directly converting this expression into a TF object. Of course, this sometimes causes some issues, and I'm going to show you that it will cause some issues and how I overcome that. Let's actually run this. Now, yeah, we can see that the coefficients are out of control, and the reason why the symbolic engine handles this with these values, these high values here, is in order to preserve the correctness of the values, basically. So it will it'll use some high numbers for precision. Yeah. But we can get rid of that when we transition into ZPK, because ZPK will get rid of everything. It will just calculate the zero, the pole, and the gain, and then reconstruct the transfer function out of that when we convert it back into TF. So we get this nice clean TF object here. Of course, you might just use sol.ki and sol.kd and sol.kp in order to plug that in and calculate the values. That's another way of doing it. But if you're lazy sometimes like me, and if you have some functions sim to TF, then this might cause some issues, but if you know how to overcome them, this can become quite simple as a solution here. So we have fs. So I'm going to get rid of this, and I'm just going to, calculate TS based on that. It's going to be feedback fs times TS, comma 1. And we need the step response out of it. So let's calculate the step response using this. And then we're going to plot. At this point, we might want to use another subplot here. So this is going to be time. This is going to be YT. There we go. Now, since we've done that, we can plot it. Maybe we could also look at the step info of the system in order to verify the settling time. So info.settling time. Info.overshoot. And then let's use the title here. TS is going to be string TSE plus overshoot string overshoot. Yeah. If we fix the typo, there we go. Now we've used the gain, the critical gain 25.7511 exactly. So we ended up in having basically this step response here, where the settling time is 3.12 approximately, and the overshoot value seems to be 17% almost. So of course we can see that we are not at the best solution yet because, well, we have too much overshoot. We don't really want to have that. And yeah, we were only focusing on the residue poles for this question, and that was the question. But if we are curious, what we can do is we can check out what the closed loop looks like in terms of ZPK. We can see, of course, slight numerical errors might occur, so that's not that big of a deal. So this is critically at 3, so we could assume that this is s plus 3 squared. But we can see that we have 3.66. If we divide that into 2, we can see that, well, we have 1.83. So it means that the zeros are closer than the residue poles here. So therefore, our dominance factor for this system is nowhere near 3. So that's for sure. Of course, we can check out what happens if we increase the gain a little bit and see how this is going to be affected. But this is just one of the possible solutions that we have. We could have even take 10 or 20 points on this branch and then show them on the right here to see if there's even a better one or not. But yeah, this is what the question asks for, so we could stop here practically, because we did obtain all the controllers that maximize the dominance factor of the residue poles. So we have the interval here, and we have shown the steps. So let us repeat the same thing for the zeros, because that's the second question. Now let's look at the zeros. For the zeros, I'm just going to change the polynomial here because I'm interested in the zero polynomial, not in the residue polynomial here. And I can basically repeat the same thing for the root locus plot even. So let me just go as far as I can go here. And I'm going to stop at this point here. So that's not going to be relevant. So what I did is I basically used PZS here. I'm going to show it in the console here, and then I did the same to it because again we will end up in a polynomial that depends on ki, and if I rearrange the terms with the ki terms and non-ki terms and divide into non-ki terms, I'll end up in the equivalent transfer function in order to analyze it using the root locus method, which I'm going to do here. And if we use GZ here, sigma omega d is the design point. We have again the same plot here, but we are building upon the next plot. So, well, let's see. Now, we can see it's a more complicated thing here, but again, we have a S term here, we can factor it out, and it starts on the right. So we can see that one pole is at the origin here, and one pole is on the right half plane, and this one tends to plus infinity and then returns from infinity back to this point, this one here, and they collide at this critical point. One of them goes up, one of them goes down. So yeah, this is a more interesting case. But here we will not have an interval as it was the case here, because you can see the root locus is bended towards right. So it seems like here the dominance factor will decrease. So we can only use this critical point. Maybe due to numerical reasons, this region could be defined, but yeah, theoretically, this point is only going to be the point because there will be a slight change, and 0.000001 will be basically decreased in terms of the dominance factor here. And from this point on, of course, you can see it will bend towards that. So even if we can practically use some interval here, I'm just going to use this critical point and I'm going to go with it. So that's basically going to be it here. But in terms of calculating the critical point of this, if you would have been in an exam, is a bit more heavy in terms of numerical manipulations here. But we could just skip that because we know that this point is going to be a critical damp point, or they will coincide at this point. You might want to use the root locus method here, but I like to switch to the algebraic method, where I use this polynomial, use the coefficients of that, normalize this because it has a different highest order term here than 1, and then equate it to something special. So let me show you that. Now, I know that the coefficients, so let's call it coefs of PZS2 depends on Ki. So let's get the coefficients here. But I'm going to normalize it so that the first term is going to be 1. And I have something else in my mind. And, well, let's call it problem 2. Coef should be equal to 1, 2 times p, and then p squared, where sims p real is given. So this is basically s plus p squared and its coefficients. So what I can do is I can solve this and look at the solution here. So what is coef? what did we do here? Oh, S. It should be S. I'm sorry, that's my bad. Yeah, there we go. Now, if we look at problem 2, 1 equals 1, that should have been satisfied. And then we have some crazy stuff here. Maybe we could use VPA 4 in order to see what it is. So we are going to basically solve this equals 2p, this equals p squared, in order to get basically the ki values. Now, if we look at sol2, it found two solutions. Sol2.ki is going to be this. So let me now use basically the placeholders here. So ki val is going to be double sol2.ki, and p-val is going to be double sol2.p-val, and we will have ki-val and p-val. Of course, it's called p, not p-val. Now we can see that there are two solutions to this, and one of them is for positive p-val and the other one is for negative p-val. And you can see that this point is actually a special point, but there exists also another point on the right half plane which corresponds to this negative p-val value, because on the negative root locus they will also collide to each other, and then one of them will go there and the other one will go here. So that's basically the reason why we have two solutions. Of course, if you're in an exam, this might be not the route that you would take. You might want to use the breaking points analysis that we have for root locus, where you just solve this in terms of ki and then take the derivative of ki and equate that to 0. That might be a simpler version, or yeah, actually they might be at the same difficulty level, so it depends upon you which you want to prefer. You might want to use that, but it's not easy to come up with this point. Even if you're using the gain condition here, you have zeros and poles, so there's a lot of mathematical work involved in order to just find out this value here. But we have MATLAB available. This seems to be the easiest one for me. So I'm going to eliminate the negative one and go with a positive one, because that's what I'm interested in here. In order to do that, index equals p-val greater than 0, and ki-val is going to be ki-val index, and the same goes for p-val index. So now ki-val is basically this, and this is going to be exactly the point that we are going to choose. So there's no interval involved here, and our dominance factor will be exactly calculated by p-val, because they will collide at this exact coordinate. So yeah, we know what ki-val is now. Let me get rid of this. Let me provide this again and this. So comment this out. And then we can just convert it back into a controller, and then maybe here. And maybe we want to display the dominance factor of the 0 as it is p-val, actually divided by sigma, but I know that sigma is negative, so I'm going to provide another negative sign here. So let's solve it. Now we can see that we have this design here. Now in this case, we can see that the dominance factor is 1.9762 for the ki value 22.8955. So yeah, we have basically acquired the controller itself. We could actually plug it in and show it like that instead of having this unknown controller, because we know exactly the point where the controller is. So it's not going to be an unknown thing here. We could just say, let's move it down here. Yeah, that should be better. So this is going to be the PID controller that we came up with Ki value exactly equal to, not greater than equal to that, with the dominance factor 1.97. We were talking about the dominance factor 3 here, which we didn't point out, but we know that it is 3 because of the fact that we ended up on this point here. So it's 3 times the real value of our desired pole pair. But here we can see it drops down to 1.97. And it was also the case for, if you look close at this solution here, you can also see when we plugged that in, that the 0 was more important than the residual poles themselves. And for that, we could just look at the ZPK value here and run this again. Now here we can see 3.66 was 1.8. That was more relevant because the overall dominance factor of this transfer function is going to be half of this value, to be exact. But here we can see that the poles are not really that affected from it, or one pole 0 is so close that we have basically again 1.976 as the dominance factor for overall, because this is the best case in terms of dominance for the zeros. And since this is not affected by the poles, it seems like we cannot beat this solution here. But still, we're going to transition into the next question, which exactly asks us to do what I did say. Basically, it asks us for the overall dominance factor. So let's look at the overall dominance factor. Up to this point, we have only looked at the residue poles on their own, the zeros on their own. So let's look at the overall dominance factor here. So that's going to be Q4. So we both have PZS and PES. So what I'm going to do differently is I'm going to choose a Ki vector here, but I'm going to use these Ki values. I have 22.89 here and then 25 something here. So let me just use 20 for the lower bound and 0.1 increments. Since it's 25, maybe we should use 30 or 40, something like that, as an upper bound. And what I'm going to do is I'm going to create some vectors. One for the dominance of the residue poles. That's going to be size Ki vec. One for the zeros, and one for overall. And I'm going to loop through each Ki value, taking Ki val element by element. And what I'm going to do is I'm going to plug that into PZS, for example, or PES. I'm going to substitute the Ki value into the polynomial, get all the coefficients in terms of S. At this point, we shouldn't have anything that is unknown, so let's convert it into a double vector. Let me do this for just 2 samples here in order to see if it's really working or not. So you can see these are the coefficient vectors. Now I'm more interested in the roots than the coefficients, so let's take the roots of them. There we go. Now we have the residue poles here. So what I'm actually after here is I'm going to look for the ratio between the residue poles or the roots of this polynomial and sigma here, so that I get basically the m value for each pole, the dominance factor for each pole. So let's divide this into sigma. That should create something positive. There we go. Now if we have two poles with dominant factor 2.97 and 1.38, the overall dominance factor for these two roots would be determined by the minimum one, by the small one. So therefore, I'm going to use the minimum operator in order to look for the actual one, because we're only interested in the nearest pole or zero or whatever it is, and we're going to ratio that for the dominance factor. So because as soon as something enters the dominant region, it will affect the response of our system, and we're not going to tolerate that. We just don't want that to happen if possible. So therefore, I'm going to take the minimum over these roots here, and that would be the dominance factor for E. If I change the polynomial, if it's going to be the zero polynomial, it's going to be mz. And now I'm actually at a point where I can just look for the overall dominance factor, which is going to be the minimum of both of them. Because I don't care if it's a zero, if it's a pole, if it's something else. I'm looking for the first one that enters the dominant region, and that's going to be determined again by the minimum. So I'm taking the minimum of minimums, sort of, but that's really what it is all about. Now, since I have something to plot here, because I have a ki vector, let me open this one, and I also have some dominance factors, maybe I should create a plot out of it to show basically what's going on here. So let me take this part here, and let's call it figure 3, maybe grid on. There's not going to be root locus whatsoever, so maybe a legend show, maybe x label is going to be ki, and y label is going to be the dominance factor. Maybe the title is also dominance factor. So I'm going to plot ki vec versus me. Let's call it red, and let's give it a line width of 2 and a display name of residue. Now these are going to be the zeros. Let's plot it in blue. Let's call it mz, and let's have magenta here, and overall could be a good point. Since I'm at it, what I can also include here, I could say val comma index and then take the maximum dominance factor solution out of this overall vector here, so that I get the value and the position in the vector, so that I can extract the ki value here. So the best possible ki value is going to be ki vec index here. So let's show ki val here. I could also plot it here, so let me maybe do that too. Plot ki value, comma value, or m index, whichever you prefer. Let's have that. Let's call it ideal. And that should be it. Of course, we have a typo. If we fix that, we have some imaginary values. Oh, we forgot to include something here. It might be possible to have the complex roots as it is the case here. So what we should basically do is, instead of looking at the minimum of the ratio of this, we should basically take the real part before we do anything to it. So that would be more safer, because we're interested only in the real value ratio. And yeah, that's something that I missed out here. So if we call it again, I plotted ME. And that one too. So did we mess up something? ME. So let me actually interesting. Let me actually look at what we're generating here for just 3 values, for example. So double roots and then real value of that divided by sigma. Yeah, it seems to make sense to take the minimum of this one here. What happens if we do the same to PZS 2? So substitute that, take the coefficients, take the roots of them, and then take the real value, divide it into sigma, and then take the minimum. Interestingly, there's no error whatsoever. MZI equals this one here. Interesting. Yeah, let's open this back up. ME, MZI should be ME. Yeah, but don't plot this one here. I guess I'm missing something, but I'm not quite sure. Because where's the red one? Why am I not seeing it? We have hold on grid on. Let's plot only ME here. Oh, yeah, I've seen it now. I somehow messed up the polynomial itself. For some reason, there needed to be 2 different plots, but yeah, now we've solved it. Sorry for this. Well, yeah, now we're talking. But here, due to the overlapping of the blue one and the magenta one, we might want to increase the stroke width or line width here to see that underneath we have this blue plot here. Now what this plot tells us is basically the same that I've concluded in the previous question, where it seems like Q3 seems to be the best possible solution that we can achieve here, because the 0 was dominating the dominance factor here, and the poles didn't really mess that up. So here we can see that at this exact point where we're working at, it doesn't touch it, or it doesn't intersect with the pole's dominance factor here. And due to the minimum that we take, that's basically not getting affected. So if we are looking for dominance factor for this system with these requirements, it seems like we only have to take care about the zeros, because the zeros for this interval never intersect or collide with the pole's dominance factor. If we would have chosen the residue poles, you can see that this would be the critical point, 25 point something. And then we also have seen that it shapes kind of a boundary, and the reason for having just 3 or greater, actually Ki greater than or equal to 25 something, which was here, 25.7511, we've seen that it shapes kind of a boundary where the dominance factor doesn't change even though Ki is increased. So you can see that is reflected here. Other than that, the dominance factor drops down. For the 0, we kind of hit this boundary. We're at the critical point, and then we return to decrease basically it. So when I showed these plots that we had from earlier, we can validate the results. They're quite different and also similar in some ways. And we can see, yeah, basically this point here is the critical point that we have chosen here. But that's not the same for the residue poles, because at that point we hit a constant dominance factor boundary, because, well, we're on the boundary and it doesn't change in terms of real value, and this distance doesn't change, so we can use Ki greater than 25.75, whereas for the zeros we have to choose the critical point, and that's the furthest point that we can get. And yeah, that's basically it. So this plot might not always come up like this. Sometimes, and most of the times, this would basically cross this pole boundary here. Then we would have basically the magenta portion on top of that, and it would switch to the pole 1 here, because that would be the minimum one. For no Ki value, as far as we can see here, the dominant factor is dominated by the residue poles. That doesn't happen here, but that's system specific. It could be the case that happens. So yeah, this is basically it here. We can see that this is, in terms of dominance factor, this is the situation that we're at in. We can choose this point here and this solution as the best dominance factor, overall dominance factor, because that's exactly the point that we get here. But the question doesn't stop here. As you can see, we're solving for Q4 here. For the overall one, which is here. And it says that, is this the best possible design? And we should answer this by using the gridding method and compare the results. What it means here is that we should basically aim only for 4 seconds and 10% overshoot and try to solve that problem here, instead of only optimizing it for the dominance factor, and then compare the results. Because at this point we assume the following: if we can achieve a the best dominance factor scenario where you can push away the zeros and poles out of the dominant region as far as it gets, you would get the best solution. This is an assumption that we took because dominant pole placement tells us to do this. But for this specific system, the question asks us to just maybe for once check out the solution where you try to optimize the settling time and overshoot directly without looking at the dominance factor. Because we assume that we have a pole pair based on settling time and overshoot. We looked for the stabilizing interval, that's also okay. And then we looked just only at the dominance factor in terms of residue poles, zeros, and then overall. But now let's forget about this. Forget about all this stuff. Go ahead and repeat this with using gridding, where I'm going to just take Ki vec from 0.1 with 0.1 increments, let's say up to 40. So I'm just taking the whole Ki interval because this is the stabilizing interval. And then I'm going to just go through each value of Ki vec, take Ki val, now at this point I want to substitute this back into the system. So what I can do, I can just get this, I can get FSS, let me just repeat that too. So I need FSS2, which plugs in the solution to FSS here, which is the PID controller itself. And I'm going to define FS based on this Ki value here. I'm going to sim to TF and then substitute FSS2 Ki as Ki val. And of course I need to maybe convert it into ZBK and then TF in order to get rid of the silliness about the coefficients here. And that should be my controller. And once I have the controller, I'm just directly going to look at the feedback here, comma 1, and then switch to info, step info, because I'm directly interested in the settling time, the resulting settling time. So TSE is going to be info.settling time, and overshoot is going to be info.overshoot, of course divided by 100, because I'm going to transition into relative errors where I have the absolute value between TSE, which is the experimental result, and TS, which was the specification, and I'm going to divide this into TS so that I'm kind of normalizing it in terms of units so that it is relative to itself. And I'm going to do the same for OSE minus OS divided by OS, because overshoot was 10 divided by 100, so this is not percentage, this is a floating point number. I did this division 2 to convert it into a floating point number between 0 and 1, and then I normalized that. So then this kind of becomes my objective, and it would be 50% times first error. So I'm interested equally in minimizing both the relative error for settling time and overshoot simultaneously. So yeah, I'm combining the errors together. I like to pre-allocate my vectors, so let me do that too. Ki vec, there we go. And this should give me an objective. And I would like to look for val index minimum, where I minimize this objective. And at that point, Ki val would be, ideally, Ki vec that index. I also have the value here. So what I can do is, maybe instead of having them side by side, let's have it 2, 1 here. Let me just bring it back here. So this would be then the second one. Hold on, grid on legend show. Ki. Instead of dominance factor, I'm going to have an objective. And that's going to be directly the objective of TS and OS. So then I'm going to plot KI_VEC and objective, of course. So let's call it objective. And then I can plot the ideal point here, which is KI val, val, and then display name objective, display name ideal. So KI val. There we go. Now let me run this. And we messed up. Probably because this is index, but this is INDX. There we go. Now, of course, if you plot the objective first, what you can do is you can look at this and then maybe chop off this unnecessary stuff here. We could start by plotting this with starting by 10, so it seems like we are on a local optima here, which is of course also shown here globally, but it's hard to pick up on, so I'd like to skip the first part here. Let's just get rid of it and start gridding starting from 10, and that should be basically sufficient because I checked the global interval, and that should be basically it. So now, interesting fact about this here is that, well, yeah, this optimization gave us a different solution. And before I talk about it more, what I can do is I can extend the upper plot so that it starts with the same starting point. And let's see what happens. So instead of looking from 20, let's start from 10 for the overall dominance factor. And there we go. Now you can see that the maybe we should just get rid of the line width of the blue one here, because now it doesn't really need to be there. Now obviously we can see now that the switching that I was talking about did happen, and it seems like here the residue pole sort of dominates the dominance factor, and therefore the magenta plot is on top of the residue pole, and then it switches from this point to the zeros, and from now on it's always about the zeros, not about the dominant the residue poles. But we can see that there is also some intersection that is going on here. And the explanation for that is the following. We can see that the root locus plot for the residue poles and the root locus plot for the zeros share a common property. They have always a pole at the origin. They start at the origin and they move to the left to a certain degree, to a certain point. So it could be the case that somewhere they will collide or meet each other, which we call a pole zero cancellation. When that happens, we are basically okay with that, so that they will get rid of their effects. So we will just be okay with that because they will cancel each other out. At that point, this dominance factor plot is not correct anymore, because since they collide, they actually don't exist anymore. At this exact point, the furthest or the closest to them, the closest pole or zero or whatever to them will be the actual dominance factor. So it arguably at this point we have maybe a better one in terms of dominance factor, But the downside to that is that it then starts to decay again back. So if it's momentarily something high, it will not stay like that if we wiggle around Ki. So that's not really, this may not be the best solution, even though it might be the best solution in terms of settling time and overshoot. So let's actually check out what the settling time and overshoot for this plot looks like. For that, I'm going to again change the type of the subplot here. This will be the first one. This would be then the third one, I guess. And I'm going to use 2 and 4 to plot the step response here. So that's going to be t, that's going to be yt, and let's get rid of that. Somewhere here, yeah, exactly here, we have this nice plot here. Let's copy that. Since we have ki val, what we can do is we can just repeat it here. Once we have ki val, then we have ts, and yeah, that should do it, I guess. There we go. Now we can see that the overshoot is exactly 10%, 9.9917, which we can just round to 10. And the settling time seems to be 3.5 seconds, with ki val 14.3. Whereas the dominant version did come up with 22.9 as the best solution here. But our solution is 14.3, a lower one. So yeah, we can see what the pole zero map looks like by looking at ZPK. Now we can see that at s equals -1, we have a cancellation. And luckily for this system, 5 also cancels out. So we are left with a very good solution, by the way. But then they start to move. So basically, there's a scenario where we can place the zeros of the controller on top of the poles of the open loop and get rid of them, and then use basically a p-type controller to design this. So there's a pole zero cancellation that works way better than expected. So this is of course system specific. This doesn't happen always. You have to always check if there's a, for example, intersection of dominance factors of poles and zeros, because that would then remind us, or that would indicate that there could be a pole zero cancellation there. And if that's improving the solution, then we are okay with that. So that is kind of the thing that happens here. But yeah, if we look at the best solution that we got here, we're a little bit off in terms of 5% overshoot, which is important in this case because we are aiming for 10%. So there's definitely an improvement here. But it means that we need to sometimes analyze the system a bit more carefully than just focusing on dominant pole placement, because there might be cancellations, and pole zero cancellations are not kind of directly addressed by dominant pole placement strategy or by its design. So yeah, therefore we can conclude that this is not the best solution, because we have a better one when we have gridding, and the only reason for that is the pole zero cancellation. In fact, both poles are cancelled out with the zeros of the controller, which is interesting to note. Now, so far so good. Now we have another task, but don't worry, that's not going to take that much, because this is actually about the PIPD controller, and we know for a fact that if you have a PID controller, you can just switch from it to the PI/PD controller. Now, about the PI/PD controller, it's actually a PID controller. That is what it is. But it has some advantages, and the most important one would be about the zeros. If you switch to a PI/PD structure, because that's what it is a structure of the PID controller that we use. If you switch to that structure, you place a PD controller in the feedback of the transfer function itself or the plant, then you end up in eliminating the PD 0 that would have appeared in the closed loop. So we did get rid of one of the zeros of the controller. So PI/PD has just 1 0 in the closed loop, not 2. It takes care of the 1 0. And furthermore, when we choose the proportional part of the PI controller and the PI/PD structure, we can adjust the 0 as we wish. The location of the PI 0, which is going to be the only controller 0 that will be present, we can move that to wherever we want. So that's also nice. So it means that in conclusion, it means that we don't really care about the zeros. You can see the problem in the dominant pole placement strategy for this system, and these specifications for the PID controller was all about the zeros. Now, if we switch to PI/PD, we can get rid of the problem of having zeros, and we can, for example, opt for this point here, because there will be no zeros that will be causing trouble, and we have to just push away the residue poles. So we can choose this ideal controller that we came up with somewhere up here, which was figure 1, that had exactly this gain value here. We can use that in order to transition into a PI/PD controller. So I'm going to exactly do that. Here, let's also indicate that this is Q5. There we go. And I'm going to use KI val equals this one here. So at this point, I'm more interested in the coefficients than the controller itself. So let's actually acquire them by using double and then subs and then sol.ki, which should still exist. Actually, sol.kp, ki, and ki val. Let's repeat it for kd. There we go. So let me run this again. These are the coefficients that I'm interested in, because this is the residue pole optimal solution. At least that's the critical value. So I'm choosing this point for the PID, and I'm going to switch from that PID into my PI/PD structure. So there's a direct relation between PI/PD and PID, and it looks like this. So we will have basically KPI and KI for the PI controller, KPD and KD for the PD controller. And let me just define them. If I define the transfer function of the PI portion, I'm going to use KPI and KI val for the coefficient there, and it's going to be 1, 0. So this is a PI controller. It has gain KPI, which I'm going to explain in a moment, and it has the exact same integrator coefficient KI val that the PID has. And then I'm going to define the PD portion, where we will have KD val S plus KPD, and then 1. So that's basically it. So we have kind of two controllers because we have separated up this PID controller into its PI and PD parts. And also we will have two feedback loops, and I'll show you how that's going to work. Now, the only thing that we didn't directly use was kpval, which is this value here. And our rule is to have the same proportional part. So we will just decompose it into KPI and KPD, but their sum should stay the same. If this is violated, then you would end up in a totally different controller and a totally different closed loop. The magic here is if you obey this rule, you won't mess up the closed loop transfer function, especially its characteristic polynomial. And when you look at our design code, we most of the time focus on the characteristic polynomial. We try to equate that to a special polynomial and then solve it. If we manage to preserve that, then it's very powerful to have this. So it is in fact very powerful. And what we want to do is we don't really care about the ratio here. So I don't care about the 0 of the PD controller here because it's on the feedback path, not on the feed forward path. Therefore, this will not be present in the closed loop transfer function as a 0. But KPI and KI-val is very important because this will be the numerator of your closed loop, since this is in the feed forward path. So if this is the case, then KPI s plus KI-val should be something special. And if I use, for example, something like KI-val divided by, let's say, z, then I would place the 0 at exactly s equals minus z. So, for example, if I divide it into 20, I could then plug in KI-val divided by 20 into this, and you can see immediately there pops up s plus 20 in the numerator, and, well, KI-val becomes just a gain value here. So therefore, I'm going to do this and use this relation in order to compensate the KPD gain so that the sum of KPI and KPD will be equal to KP-val. So therefore, I need to calculate KPD. That's going to be like this. So you see KPD plus KPI should be equal to KP-val. Now, since we have defined our controllers, let's call it TSI, TS internal, because we will have two feedback loops. Let's call the feedback command. Let's have GS, and FS or FPD is on the feedback path. Then we will have TS, which is the actual feedback, and it will use FPI and the internal feedback loop and comma 1 as the feedback branch. So we end up in using this TS value here. So let me directly generate this plot here. So what is it now? Figure. Seems like it's going to be 4. There we go. We don't really need that. Step response, get the step info, all that stuff. And yeah, it should be it. Well, let's look at the title here. We can see it has 4.16 settling time and 6.3639 overshoot. Now, in terms of settling time, we're at a good spot, but our overshoot is too low. But keep in mind that this is not the only solution that we can come up with. We can change the KI value, we can increase the KI value a little bit to improve on that. Maybe it will improve. Let's see. For example, what happens if I multiply it by 2, because I can. So let's run it. And I've just designed it so that it will update all the necessary stuff here. And yeah, you can see that we can basically hit the 10% overshoot value with a little bit more, 10.44. But keep in mind that 3.5 seconds is the only solution for the pole zero cancellation PID controller, whereas we have here 3.8 sort of. So I can maybe toy around with it a little bit more, like 1.5 maybe. Maybe it will increase the accuracy here. There we go. We have 9.5% overshoot and 3.94. So it seems like 1.75, for example, seems to be a good candidate here. So I'm just toying around with it because I can. Because I'm not pole zero canceling, it's not directly restricted to that. And because of the fact that at some point I can push away the poles, and I did care about the zeros, I can basically maybe get a better solution out of this. And you can see I can maybe hit the 10% mark if I, for example, try 60 something, I don't know. I'm just trying to adapt it a little bit more, to perfect it a little bit more actually, to get almost the effect that we are looking for. I don't know if I calculate the objective, if this is better or this is better. You could maybe also even do that in order to see if it's really better or not. But it seems like if we care equally, 0.2 is not that high of a difference. Maybe 1.65 is even better. I'm just having fun at the moment to try to hit 10%. Yeah, well, you can toy around a little bit more, but I could stop here because we have 9.9221. I'm not going to care about this anymore because that's 10% practically. And 3.88, which is a bit faster, 0.3 seconds faster than this system here. But yeah, we have even more options than this, so we can go even faster and have a little bit less overshoot, so that's also something nice. But yeah, we can see that the PIPD controller has a totally different structure to it, because ZBK TS, it will show, as you see, I have placed S plus 20 myself, and then I have just adapted the values so that the effect of the residue poles are a little bit different or less maybe, so that my overshoot and setting time requirements are almost met. Now the problem or the issue here is that this is of course not ideal at all, because we have still a dominance factor of 3, which is not quite enough. But it works because, yeah, practical reasons and stuff, but yeah, this is not the ideal solution. Ideally we would like to have at least 5 as the dominance factor, but with these zeros present, the PID controller was only able to handle it if it would cancel the poles and zeros out. Then it came up with a perfect solution, but that's nowhere the standard or average system design results. So this is kind of very specific to this system, where we can cancel both poles and zeros so that we get to our desired point with using gridding, which is also rare, not really that common. But yeah, this is basically the explanation to homework 2. Hope that it was very helpful, and hope that you did have some did learn something from it. Yeah, that's basically it. See you in the next videos.